Okay, let's start again. So welcome. This is week 10 actually. We are about halfway through the machine learning class, which is great because it's a lot of work you guys have put in, right? And you guys will see going forward, the algorithms will be easier as we keep going. And you will see this this week with SVM, new algorithm, right? So yeah, so remember, this class is going to be focusing on machine learning, right? And after this, we'll take a break. And then depending on the interest, we may do a deep learning track as well, right? So, so we will see. We will see how the class is and what the reception is. Yep. Good, guys. Any questions before we get started? Right, so I just emailed you guys slides. There's one slide I emailed for this, today's session and next week. Basically, it's a classification slide. So take a look at it. We'll go over this. All right, guys, any questions before we get going? Otherwise, I will do the usual. I will do the review, and then we will kind of answer some questions. Okay, excellent. Now, where are we in the overall scheme of things, right? So, right, as you see this, right, we've done a lot of prereq work. And now you're going to see all of that is starting to pay off, right? And it's kind of hard to make a case when you are doing this because like you're kind of learning this in kind of abstract. But now we're actually doing the algorithms. You will see why we spent some time doing this. Okay, so we started with classifications. Now, you guys have done regressions the week before, and this is classification. So let's kind of quickly go over some of the classifications and answer some of the questions you must have, right? So, interesting, looks kind of weird. Okay, so let me check why this is a little unformatted. Okay, that's fine. That's on me, right? So basically, what is classification? So classification is basically you are given a data point, and you need to make a decision if it's A or B, right? Usually we do a binary classification like 0 or 1. For example, we will say A means 0, 1 meaning B, right? So that's why usually a lot of the classification algorithms work. When you do especially binary classifications, it's a one or the other, right? So I always say kind of, right? Kind of like this, right? So I've been starting to use Legos for my training. So, right, if I gave you a box of Legos, right, can you separate them, right, green or red, basically, right? So this is a binary classification because my choices are basically green, green or red, right? So basically what we do is we say, okay, if it's 0, that means green. If it's 1, that means red. So that's how we sort of map the binary classification into our arbitrary choice of class. It could be like a, right, spam, right, not spam. Right? So anyway, so right, so you can understand, right? So that's what we do. All right, so basically I gave you guys a few readings so we can understand classifications. And then one of the things we need to understand is classification metrics. Now, I know this is a bit of a reading, right? And if you didn't get through all of this, that's okay. As you do more classification algorithms, you can go back and revisit these. Because today we are going to look at things like confusion matrix, right? And I will explain this a little bit as well, okay? All right, guys, so any questions from the reading, right, from last week? So question for you guys, how is classification different than regression? Can you guys tell me? How is it different? So what did we do in regression? Remember the lab before? What did we do in regression?
Well, you have to train things in regression.
Yeah, you can go ahead and type in the chat window, please, if you don't mind. Right, so regression is about predicting numeric values, meaning numbers, right? Remember, that's what you guys did. You guys predict the house prices, stock market, right? Whatever you guys have. But classification, we are predicting one or the other. Remember, say same example, right? One or the other, right? So kind of keep that in mind. Yeah, exactly. Now, other question is, what's the difference between binary and multi-class? Right, so let me give you an example. Let's see if I can pick one a different color. All right, so I just showed you guys binary, right, red or green. A multi-class is going to be more than red or green, right? So I'm, for example, right, I'm adding more classes. So for example, right, if you, let's say you are doing a, let's say, it's kind of a grim example, but like, let's say you're doing a cancer analysis, right? So you're doing like level 1, level 2, level 3, right? Or you are, classifying a supporting ticket. Like when a consumer opens a ticket, let's say you have three categories, right? High priority, medium priority, low priority. So those are what we call multi-class. Yep, exactly. Right. So we are going to start with binary because that's a straightforward one, and then we will move on to multi-class later. Okay. So as you guys are reading, what are some of the classification algorithms can you guys think of? Can someone tell me the answer? Some of the classification algorithm, there's more than one. Yep. Actually, k-means, I would say, it's a clustering algorithm. I believe you are saying k-nearest, right? So k-means is clustering. Exactly, k-n-n. So that means k-nearest. That's the classification. XGBoost, absolutely, yep. Any other guesses, guys? Any other classification algorithms? Right, remember it's in our all our algorithm sheet, right? Remember we have this classification algorithm, exactly, right? So things like SVM, logistic, right? What we are doing is classification, naive-Bayes, KNNs, exactly. So there are lots of algorithms. Now the question is going to be, which one should I use, right? And this is where once we, I'm going to wait to tackle the question, for one more week until we have a couple of algorithms, under our belt. Then we will go back and start evaluating what's the best algorithm, right? So short answer is we are going to use cross-validation to do this. But before we jump into that, I want to for us to understand different algorithms. Yeah, good guys, very good. So we're going to do a quick review checklist, right? Now, how do we test the accuracy of the algorithm? Right now, this is interesting. Remember, in machine learning, whenever we do machine learning, we need to have one, at least one metric to optimize for. Remember in our previous example, we looked at the error, right? The building and tipping example. My algorithm tried to minimize the error, right? So, and that's what we try to optimize. Because remember, I always say, let's say you are driving from point A to point B, you are trying to optimize for something. Maybe most of us try to optimize for time, right? Because I want to get there as quick as possible, right? Sometimes you want to optimize for distance. For example, right? I mean, maybe the fastest route is not the shortest route. You can, right? Maybe, for example, let's say you're going from point A to point B. Maybe you take a freeway. That's the fastest, but you're gonna, maybe you are, traveling more, a few miles extra. But if you take the back roads, maybe you can get there, in the shortest distance, but may not be the time because you have signal lights and stop signs and so on, right? So pretty much everything in life we try to optimize for something. so machine learning same way, right? What are we optimizing for? In the previous algorithm, we try to minimize the error because the error we can measure, right? For example, in the tip example, let's say the actual tip is $12 and my algorithm predicted $10. That's a gap is $2, right? Now I want to measure, right? My goal is to kind of bring this all together, right? So actual, right, predicted. So again, I want to get this as close to as possible, right? May not be zero. I mean, if it's exactly the same, that's a perfect prediction. May not happen, right? So our goal is to get as close to the actual value as possible. Okay, so we look at confusion matrix and accuracy, all this stuff today as well. Okay, now if you don't get some of these in the first go, like what is ROC, AUC, don't worry. But remember, that's why the classification is a little longer reading. So like I said, if you're a little behind on this one, don't worry. You can go back and catch up on this one. Yeah. So it's because especially when we introduce a new topic, there's a bit of a reading, right? So don't let that put you guys off. So do as much as you can. And as we go through the algorithms, you can always go back and refresh. Yeah. Good, guys. So let's start with logistic regression. You know, I hope you guys have done the reading, right? So this part of classification, right? Logistic, and gave you guys a few things to go over, and and a few exercises, right? I think I gave you guys how many? 1, 2, 3. Yeah, good. So let's do a little quick theory, and I will do review of the labs as well. Okay. All right. So classification, right? I sent you guys these slides, this morning, just one slide here for the classification, right? So again, classification. What's the idea of a classifier? You give mixed input. Classifier should be able to classify them into appropriate buckets. So here, here you can see mixed input is going in. It could be anything, right? It could be emails. And then the classifier basically says, okay, these are spam emails. These are good emails. This could be credit card transactions. The classifier might say, these are good transactions. These are fraud, right? Whatever, right? So the classification, right? So we're going to start with logistics. Very simple classifier, but very effective too. The reason we still study logistic is it's a pretty powerful algorithm, right? So you can see the algorithm map, right? We are in supervised category. What is supervised meaning? We are training, right? We are training and predicting, right? So that's supervised. And we just did regression, and we only looked at one algorithm, linear regression, right? And we are moving on because I want to cover classifications, and there are other algorithms. We'll come back to regressions later, right? So we just did linear regression the week before. Now we're in classifications, so we're going to look at logistic. Okay. Now, okay, question about slides. Very quickly, if you're not getting the slides, you want to go to the guide, and there's a section for you to sign up, right? So you see here to receive class materials, follow the instructions, and sign up to get the slides. And then it'll send you guys all the slides, right? So what the system will do is it'll send each module as an email. So after you sign up, check your email and you see the slides. Yeah. Okay. So hope that makes sense. All right. So the example I kind of use is, let's say we are doing a credit card application for a credit card, and let's say we're only using our credit score or like a FICO score to evaluate if I get the credit card or not. So here's some data. This is actually real world data. I kind of chopped off some of the columns just to make this simple. So my input is credit score and approved, yes or no, right? That's the answer, okay? So if I plot this, here's my credit score at the bottom, right? So you can see 300, 400, right, 800. And then my graph looks a little weird because there's only 2 states for the approved, yes or no, that's it. There's nothing in between, right? So we look at this, 0, 0, 0, and then 1, 1, 1, right? Pretty intriguing, right? So this is definitely not linear regression. Remember, we have family linear regression, so this is not linear regression. Why? Because linear regression expect values can change smoothly, right, or continuously. This is not continuous, right? This is discrete. This is 0, then jumps to 1. Okay. So how do we solve this? All right. So this is where logistic regression comes in. Right? The reason we call it regression, right? So we looked at linear regression first. So linear regression, you guys gave a bunch of input and gave X is input, Y is the output. Y is just a number, right? It could be house prices, stock market, what have you, just a number, right? So, and these are what we call continuous value. Classification, basically we are going to give an input. It's going to give, let's say it's a binary output. Let's say, yes or no answer, right? Or Y1 or Y2. These are the output classes, right? Logistic is kind of in between. That's why it kind of confuses people. We give input to logistic, the output is still a number, right? So, but that's a special number. It's actually a probability between 0 and 1, right? So that's why it's called regression, because we are still giving a number at the end, but it's a special number. It's a probability number between 0 and 1. Is that gonna make sense, guys, right? So with that information, let's look at this one, right? Remember, logistic is a pretty old algorithm, right? Invented by David Cox, right? Sir David Cox, I should say, right? And you can see, right? Very, very accomplished man. So the reason, so the algorithm is pretty, fairly well established and fairly old, but still works great, right? So that's why we use it, right? So again, we use logistic user regression algorithm, but we use it for classification, right? So again, I'll show you guys why we do this, right? So here's a logistic equation. So it looks a little complex, but if you look at this, it's pretty simple, right? We just, exponential, right? So the reason is that this formula, right? The output, no matter what the value of x is, the output is always between 0 and 1. And this is called a sigmoid graph. Very, very important function in machine learning. And also, if you can see it in if anybody's doing some reading on deep learning, you will find it there as well. Very, very important function, right? So the function behaves like this, right? And you see how the function behaves, right? It's basically, this is the equation. So as you can see, as our input values are kind of approaching like large numbers, it's kind of basically converging towards 1. Right? And the input values are getting large negatives, it's approaching 0. But it's always between 0 and 1. So it doesn't matter what your input is, you can always be sure output is between 0 and 1. Now that's great, because if you can map this, right, to my equation, look at this, right? So the S curve kind of, so by the way, this is called S curve, right? Because it looks like a sigmoid, that's called sigmoid curve. It looks like an S, right? S curve. And if you sort of superimpose the S curve, it kind of maps to my problem, right? But thing is, this is a continuous function, meaning it's a very smooth function, right? But my outputs are 0 and 1, they are discrete. So how do we map the continuous function into 0 or 1? Okay, let me walk you through an example. And I'll explain how this is done. Okay, so remember, this is my equation, right? What's my sigmoid equation? Is this guy, right? And I sort of rewrote this, right, to basically kind of right, see this like this way: y equal e to the power something, and 1 plus e to the power. So y is my output. I'm trying to predict. X is my input. These guys, beta 0 and beta 1, they are coefficients. Now we know all about them, right? Because we did this in linear regression, right? These are coefficients. Now, let's say I did this math earlier. I had calculated a value for beta 0 and beta 1 to be these numbers, just numbers, right? These are coefficients, just numbers, nothing else. And let's say my input credit score is 700. So, if you live in the US, you know all about credit scoring, right? It's used for basically to predict whether you get mortgage, you get a loan, anything. So it's very, very integral part of your credit worthiness, right? So let's say my input score is 700. I plug it into the formula, right? So you can sort of follow the numbers, right? So the beta 0 is this guy, right? And then beta 1 is this guy. And the main input is input is X is input. You can see that, right? 700. So you plug it in, right? And the answer is 0.84. So we're going to look at in the graph, right? If the input is 700, the answer is 0.84. Okay. So that's what the sigmoid function is telling me, or the logistic function is telling me. But remember, I want a yes or no answer, right? But all it's giving me is 0.84. So the way you have to look at this is, right, kind of like, so it's a probability of you getting your credit card. So if I say you have 84% chance of getting a credit card, right? Would you say the answer is yes or no? Probably you say yes, right? And you're kind of thinking like because it's basically a threshold. So I'm saying, okay, anybody scoring above 50% is a yes. Anybody scoring below 50% is a no. So that's my threshold. So this is called threshold. All right. Now this is a default threshold, but your threshold can be anything, right? For example, let's say this is an exam. Somebody scoring, this is the exam, your score, and whether you pass or fail. You could say, to pass this course, you need to score above 80%. That's your new threshold, right? So threshold doesn't need to be, exactly in the middle. So for example, you can say, if your exam score is 700, your score is 84, it's above threshold 80, you passed. So you can change the threshold to anything we want. That's under our control. So what logistic give us, it'll give us a number, and then we basically compare the number with the threshold, and then we say yes or no. If it's above, yes, below, no. So is that gonna make sense, guys, right? So that's how we are mapping a continuous value into basically a yes function, yes, like a binary value, right? Yes or no. Very important to understand. Does this make sense, guys? Right, kind of a concept wise. Oh, question from Chaitanya, how did I determine these numbers? I actually ran this logistic regression before already, so to determine the numbers, right? So I cheated a little bit, right? So I actually ran the logistic regression, and then that gave me the numbers. And based on this, I plot this graph. Yeah, yeah. And you guys are going to do this soon, but right. So for now, I just want to show you an example. Yeah. So what's the basic takeaway out of this? Logistic, right, is basically based on this, this probability function, right? And right, so, and why it's a probability function? Because the logistic always guarantees the output is between 0 and 1. Okay, armed with information, right? We go and we superimpose the logistic curve, right? And then the threshold is something we can control, and this is what the algorithm will figure out, right? So the threshold algorithm will figure out, okay, you can see, right, as you can move the threshold, your results will change. So how do you find the perfect threshold, right? And that's what the algorithm learns, right? So where should be, where should be the cutoff point should be, right? So meaning everyone below the cutoff point is 0, everyone above the cutoff point is 1. Yeah. It's like, like a SAT score, I mean, I don't know if they still do it, but like universities, they will say, every year they will say if you score more than this SAT score, you are qualified or you're eligible, right? If it's below that, you don't qualify, and that score keeps changing every year because it's based on the overall distribution of the SAT scores. They determine that, right? Anyhow, all right, guys. So is it gonna make sense how we map the sigmoid into yes or no answer? Yep. All right. So here's the idea, right? So basically, in this case, I'm giving a credit score as input. So my logistic regression gives me yes or no answer. The input can be more than one, right? And some of you have already done this labs, right? It could be, for example, instead of just credit score, I could maybe input credit score, income, and maybe, if I have other debt. Same formula, right? It'll come back as yes or no. All right. So here, here's the example you guys did, right? So GRE, GPA, and rank, these are my input data. This is like a college admission data. GRE, GPA, and rank are my input, and this is the output. Remember, output is basically 0 or 1, right? That's it. So if I do logistic regression on this one, and this is my output, right? So you can see this is the input, actual output, and this is my prediction. And you can see some of the prediction, most of the time it matches the output, but sometimes I mispredict, right? See the ones on the yellow, those are misses. And that'll happen, right? So when in machine learning, we don't get 100%. So yeah, that's part of life. Our goal is get the prediction as close to the output as possible, right? That's what the algorithm is going to learn. So now you guys know how all that works. All right, so let me pause here for a second, guys. Any questions so far? Logistic regression, kind of, right? Important to understand the mechanics. Any questions, guys? Please go ahead and let's take a pause here for a minute. Any questions? So question was, do we still use logistic? Yes, because for some problem, logistic actually works really, really well. And especially in like medical community, like things like figuring out cancer, not cancer kind of thing. A lot of the doctors, actually learn logistic regression in their statistics course, right? Because it's used pretty heavily over there. Yeah, exactly. So let's see what some of the questions are coming through. Let me see. Right. So right now, logistic, the vanilla logistic regression can only do binary. Binary meaning, right? As I said, one or the other, right? Because remember, that's an easy mapping, right? 0 or 1. There are extensions to logistic regression that can do multi-class. When I say multi-class, you mean, right? I have, so let's say 3 or 4 class, more than 2 classes, right? We won't cover this here, but I will give you guys some link so you can kind of read about this. But default logistic is two class problem. We call binary class problem. Yeah, very good question. Yeah, so we'll focus on binary for now. And one thing you will find is, in real world machine learning, a lot of the times you basically deal with binary classification problems. Yeah. Question for DNN. So DNN is basically stands for deep neural network, I believe. It can do both classification and regression, right? So that's more on the deep learning side of things. But yeah, so a DNN can do both classification and regression. Yeah. All right. So threshold. Right. So threshold, right? So I mean, yeah, right. So remember, what do we use threshold for? So the equation, right? Exactly. So the equation is pretty much determined, right? Then we adjust the threshold to basically, right? And you can control this one, and these are what we call hyperparameters, meaning we can actually adjust the threshold to match our needs. And that's what I'm going to cover in the next section. Yeah, so algorithm also comes up with the default threshold. I think the default is 0.5, but you can set it too. And then based on this, it'll learn, right? Because the S-curve can be tweaked, right? It doesn't have to be like this. It can be like maybe slightly, rising pretty sharply, things like that, right? So again, these are coefficients the algorithm will learn during the training phase. Yeah. So yeah, exactly. So the way we are rewriting this basically just to kind of make it easier, right? So given X input, Y output, you can sort of rewrite the equation, right? Kind of like that, right? So rewrite the equation this way, right? So you can sort of look at this one, right? How it's done. It's basically called log of odds. Basically, what you're doing is you're kind of calculating the probability of something happening, right? That's the essence of this. There's some stats theorem, right? So there's a stats theorem behind this. So basically what the logistic is telling you, it's not telling you yes or no. It's telling you the probability of something happening. So when it says 84%, it says the probability of me getting a credit card is 84%. Whether it's a yes or no, it's up to us, right? For example, if my threshold is, let's say, 50%, scoring 84 is a yes. But what if my threshold is 90%? Then scoring 84 is a no, right? So let's say, we have a very highly exclusive credit card, right? One of those black cards or gold cards or whatever, right? And let's say when they run this run your credit score, they say you need to score more than 90% to get this card because this card is so exclusive, right? So even though you scored 84%, you're still a no, right? So that's depends on threshold, right? So that's why threshold is a very important factor because that's how map a smooth curve into a yes or no decision. Yeah, good questions. Good question. If we have less data, small set of data, can we still use logistic? Actually, yes. And this is one of the reasons logistic is actually pretty good. It doesn't need a lot of data to train. It can learn on reasonably small amount of data, and that's why it's pretty popular because if you have small amount of data sample, logistic can still give you decent results. Yeah. Some of the other algorithm we will see like random forest and things like this, they will need a little bit more data, right? But logistic can work with small amount of data. Yeah, great question. Yeah. What else? Right. So the when you do scikit, they will use a resolver called LBFGS, right? It's an algorithm they use. I forgot what it stands for. I need to go look at the documentation, right? It's basically, remember, in some cases, right? So the question was, my algorithm didn't converge. That could happen because some data, logistic may not find a solution, right? Yeah, that could happen too, right? And then if that's the case, you can fiddle with some of the input arguments a little bit. You can tweak the knobs a little bit. But if it doesn't, right, then you have to go find another algorithm. And that can happen. And that's why remember, we will do this a little later, right? Once we have a few algorithms, once we know a few algorithms, I'm going to have you guys actually evaluate a few algorithms for a problem, right? So Remember, we are just starting, right? Logistic is the first classifying algorithm you're doing, and it's a very simple algorithm, right? That's why we are starting with this one. Great, guys. Great questions. Okay, thank you for asking. All right. So now I showed you guys we are predicting 0 or 1. Now, how do you measure the accuracy? Because in the regression, I could simply subtract, right? Remember, my estimated tip was $13, actual tip is $10, so my different delta is 3. I can subtract and find out. But here subtraction doesn't make sense, right? Because the only allowed values are 0 and 1. So subtraction is always 1, right? Either you predict 0 or you predict 1, right? There's nothing in between. So we need a different way to evaluate this algorithm, right? And that's where we are going to come into something called confusion matrix, right? So I'm sure you guys have did some reading on the confusion matrix, right? I want to make sure I gave you guys enough information here. Introduction of classification. So go back and read this. Confusion matrix, very, very important. Despite the name, it's pretty straightforward, right? Once you understand the mechanics of it. And that's why I want to kind of quickly explain to you guys, because we will use this quite a bit, okay? So let's look at the confusion matrix. So the way I look at a confusion matrix, right, is basically we are testing a classifier. So imagine this, right? So let's say I'll just make this very simple, right? So let's say I had to predict between 2 classes. I'll just do my Legos again, right? So your choice is between predicting 2 classes, right? Red and green, right? So let's say one is A. So your choices are, you can predict either A or B. So now I'm sending you, so this is A row, right? So everything in this row is A. So I'm sending you 6 A's. Okay. I'm sending you 6 A's for testing. And I'm asking you to classify them. And out of 6, you correctly identified 4 as A, but you misidentified 2 of them as B. Remember, we are testing, right? I'm testing your algorithm, right? So I'm sending you 6 A classes, right? Remember, this algorithm predict 4 out of 6 as A, which is correct. That's why it's in green cell. And the 2, it mispredicts. Okay? So as you can see, the accuracy is 4 out of 6, right? So 60% accuracy here, okay? And it missed 2 out of 6, right? Because I sent 6 as input, 2 incorrect, right? So that's error. Okay, so that's A. Let's also do B. So I'm sending you 4B. Now the algorithm, out of 4, it correctly identified 3 as B. Remember, this is the B column, right? It put 3 in the B column. So accuracy here is 3 out of 4. That's good. But 1 is misidentified as A. So is that going to make sense, guys? So the way to read the confusion matrix is like this. The rows are actual. The columns are predicted. Once you get this, confusion matrix will make a lot more sense, right? So again, right, so because remember, in our classification, right, classifiers are not perfect. So when I test them with different types of inputs, some A, some B, they give me different results. And when you look at the cells, you see, right, they're like true positive, true negative, right? So true positive meaning what? Algorithm says it's positive and it's true. Right? Algorithm says negative is true, right? And then the other ones are false negative and false positive, right? I'm sure when you guys listen to news or stats, you probably encounter this term. People say true positive rate, false positive rate, right? This is what it means. So basically, they are generated from a confusion matrix. Yeah. So let me give you another example here, right? So let's say I have a perfect confusion matrix. My classifier is perfect. Okay. So I have 2 classes A and B, right? I'm testing my confusion. Right? Remember, this is actual A, actual B, and this is predicted and predicted. Okay. So let's do the exercise real quick. I'm sending in 10A as input. Remember, this is perfect classifier, right? What do you think the values for here and here is going to be? Can you guys type in the chat window? Take a minute to think about this. All right, I'm sending actual 10A actual. This is the A column. This is a B column. On a perfect classifier, what will it look like? Can you guys tell me on the chat window? Good, good, good. I need a few more examples, please. Yep. Yep, good. So remember, perfect classifier, right? Meaning I sent 10 A's, so it's going to predict all A's under the A column and 0 B. So it's going to be 10, 0. Why? Because the algorithm is perfect. Same thing, right? Now you look at this B, I'm sending in 20 B's. Now you guys can send where that's going to be, right? So it's going to predict everything under B as 20. It's going to correctly classify all the B's under B and 0. Yeah. So on a perfect confusion matrix, diagonals will be 100% coverage. Everything else will be 0. Does that make sense, guys? Huh? So A and B, right? Two class problem. On a perfect confusion matrix, you will see only diagonals have numbers. Everything else is 0. Okay. So confusion matrix doesn't have to be, right, two class problem, right? So this is the answer, right? It can be a 3-class problem. No, as number of classes as you guys want, right? Because just put them in rows and columns. So here's my another confusion matrix. I'm classifying animals. But those are my input data, right? I am sending in 8 cats, 6 dogs, 13 rabbits, and this is what the algorithm is predicting. Cat, dog, rabbit. So for example, I send 8 cats. Out of 8, it predicts 5 correctly as cat. Remember, cat, right? 5 correctly. 3 it misclassifies, right, as dogs. So what we're looking for is we're looking for diagonal numbers. The green cells, they had to be high. But it's not perfect, right? Because we see some other numbers all over the place as well. Now, this classifier, which animal this classifier is good at classifying? This is a 3 classifier, right? I mean, if you look at this, right, it's like a 3 classifier, right? I have 3 classes. So cat, dog, and rabbit. Look at the confusion matrix. Tell me which animal this classifier is good at understanding. Is it a cat, dog, or a rabbit? What do you guys think? Yeah, seems like rabbit is doing pretty well, right? Because see, I sent in 13 rabbits. Out of 13, it correctly classified 11 as rabbits. Only 2 are misclassified as dog. So the accuracy is pretty high, right? So 11 out of 13, it got right. Good, good. So you guys are getting the hang of this, right? Okay, so which animal is not doing so well? That's okay. Right? So you actually answered the question before you asked the question, right? So dog is not doing so well, right? Because remember, I have 6 input dogs. Out of 6, it's only identified 50% correctly as 3, right? So this is the correct cell, right? The green cell is the correct cell. All right. So does that kind of make sense, guys? So now you guys know how to read the confusion matrix, all right? Any questions on this one, guys? Very, very important to understand. All right, confusion matrix. And pretty much all classifications, we will use confusion matrix to evaluate our algorithms. Even in deep learning, right? I just finished teaching a class at deep learning last week, and they didn't know what a confusion matrix was because I asked them, okay, they ran a classifier, and we got some results. I asked them, all right, guys, create a confusion matrix so we can evaluate them. They don't know how to, right? Because then I later learned they jumped into deep learning without doing machine learning, right? So they don't really understand a lot of the machine learning concepts. So they kind of, right? They kind of, because deep learning gets all the buzz, right? So, and that's why I always say to study deep learning effectively, you need to start with machine learning, right? Because a lot of the concepts come from machine learning, right? So, good. All right, guys. So that's confusion matrix. Any questions on the confusion matrix? Yeah. So let's see. Go ahead and type in the chat window, guys. So your question was why is yes, we will, yeah, exactly. So confusion matrix is one of the metrics we are going to use to determine different algorithms. Right, exactly. And again, we will get to that maybe in 1 or 2 weeks when we have learned a few algorithms. And each algorithm is going to give you a different confusion matrix. Yeah, yeah. So exactly, right? So once you have confusion matrix, there are a lot of metrics we can calculate from it. And that's why this is very popular, right? So question was, how do we know? I see the question from Vasilios, how do you know which algorithm and which features, right? Now, I'm going to wait to answer this until we get to maybe in another 2 weeks, right? Because I want to have a few algorithms, study a few algorithms so we can actually go back and evaluate. Because there's one of the exam for 1 week, we have a break week coming up. I'm going to give you guys an exercise. You're going to try 3 or 4 different classification algorithms and pick the best algorithm. And when you guys are doing this, you will understand how to evaluate algorithm and how to choose features. Yep, and we'll talk about that then. It'll make a little bit more sense. Okay, yeah. So coming up soon. Now, when you have confusion matrix, right? There are a lot of things we can interpret from confusion matrix, right? For example, right? For example, how do you say false positive meaning, right? Like true positive, true negative, false negative, right? These are basically it has real world implications. For example, false negative may be meaning, right? Let's say a patient comes in for a diagnosis. Let's say the patient has cancer, but the algorithm clears them. This says, no, you don't have cancer. False negative, right? The algorithm says negative, but it's false, right? So things like that, right? So, and you can look at some of the real world cases, right? And also, and this happens in interviews as well, right? Interviews as in, like, for example, let's say you went to a job interview, you think you did pretty well, right? But they didn't hire you. And this happens quite a bit, right? So, especially, companies like Google and Facebook. So that's basically all false negative, right? So they chose not to hire you, even though, you may be qualified because, you maybe missed some of the benchmarks, whatever, right? Anyway, so kind of read this to understand what are some of the real world implications, right? So, all right. So now that we have confusion matrix, I'm going to show you guys a few metrics we calculate from this. And let's start with accuracy, because this is very simple to calculate. And this is what most of the time we use. So I see the chat comment here. Right. So let's look at our confusion matrix here. So let's say I'm positive and negative, right? Very simple. Positive and negative, A, B, doesn't matter, right? Just 2 classes. Positive, negative, A, B, spam, not spam. So I have 200 data points total, right? And out of the 200 data points, this is my test data. Out of 200 data points, 120 is positive, 80 is negative. Right, let's say AB, just to keep it simple. AB, AB, right? That's it. So I'm sending 120 A's. Out of 120, it finds 90 as A correctly. 30 are misclassified as B. Now, when I send in 80 B's, out of 80, 70 is correctly classified, right? 10 is misclassified as A. So now we know how to read this now, right? So let's calculate some scores. So accuracy, and this is the most common used term. So what is accuracy? Accuracy is basically, right, what's my total and how many did I get right? So the green cells, right? So we look at the equation, true positive plus true negative, meaning now these are the correct classification, right? How much is true positive? Look at the cell. True positive is 90, right? 90 here, right? True negative 70, right? Out of 200. So my algorithm is 80% accurate. What's the error rate? It's the opposite of this, right? If I'm 80% accurate, my error is 20%. You simply add up the misclassification, right? So this is accuracy. Easy to calculate, and most of the time this is what we use. However, accuracy sometimes may not be enough, right? So here's an example of this. So here's right. Let's say this is a cancer evaluation. I had 2 patients that are positive. They actually have cancer, 98 people are negative. So out of the 100 sample size, right, 98 negative, 2 positive. And look at the algorithm, right? The algorithm correctly identifies everything who's negative. So it clears everybody who's negative. Okay. And there's no false positive. That's great. But on the positive side, it only identifies one person as positive. The other person, it falsely clears the person. Right? So out of 2 people, it gets 1 right, 1 wrong. Now, if I calculate the accuracy, right? Accuracy is what? Look at the green cells, 98 plus 1. So it's 99% accurate, which is very good, right? So you can say 99% algorithm pretty good. However, right, this is not a great scenario, right? Because we actually had a patient who actually had cancer, right? That basically the algorithm said, no, you're fine. You don't have cancer. So this patient is now not getting a treatment, possibly, get into, some, maybe even die, right? That's a very grave mistake. So what if so we don't want this to, we actually want this to be 0, right? Meaning, we want the algorithm to calculate everybody who's positive as positive. So when I tweak the algorithm to do that, I may have, have a side effect. Maybe the algorithm will, kind of, may not have the perfect record here. So maybe out of 98 people, it incorrectly classified 5 people as having cancer, even though they don't have cancer. The algorithm said, no, you may have cancer, right? Because remember, when you tweak this dial, right, you can just increase one metric without affecting the other, right? It's kind of like a little, right? Everything is connected. So when I try to sort of get this right, because this is very important to me, right? Because we want to make sure all the positive cases are identified. Same thing, coronavirus, right? And any disease. But what if this scenario, guys? Like, what if I'm healthy, but the algorithm says I may have cancer, all right? So that means I have to go under further diagnosis, but at the end I will be cleared, right? Because I don't have cancer, right? So algorithm kind of falsely predict that I may have cancer, so they will do additional tests, and then eventually they will say, okay, you are clear. So yeah, so this is this is inconvenience, right? Meaning I had to go in for extra testing. It's cost in the hospital or clinic to do extra testing, but at the end, no harm done. So I would rather have this algorithm, right, being a little bit more conservative than letting patients lapse, right, fall through the cracks. Is that going to make sense, guys? Right? So that's the story I'm telling you, right? So what's the moral of the story? Accuracy by itself may not be enough, right? Because remember, the algorithm is 99% accurate, right? That sounds very impressive. Because what if right, most of your people are negative, and it's that's where it's getting most of the score. But let's say it's only doing just 50% on the positive. That's a very bad algorithm. Anyway, so if you look at the next few slides, I'm not going to go through them now, but if you look at the next few slides, there are other metrics people have developed to identify this this problem, right? So these are called precision and recall, all these metrics, right? So look at the other few slides. Look at the equations and how they are calculated, right? And in some cases, you may have to use those, especially when the data set is imbalanced. And we will look at some of these in a later towards our course, right? Because in real world, a lot of the data sets tend to be not balanced, right? It's going to be like this, right? So look at the next few slides. Kind of look at the equations and kind of see how they're these are different metrics we calculate. There's like F1 score, right? There we go, right? F score and all this stuff, right? So all these are kind of more advanced metrics. But for now, we can simply start with accuracy, right? So let's start with accuracy because that's an easy metrics to understand and calculate. And in further down the line, we will calculate more and more more complex metrics. All right, guys, that's basically the basic idea in begin classifications. Any question on this one, guys? So confusion matrix, once we have it, right, from there we can calculate different attributes. Right? So I just showing you guys a few of those. Okay. So yeah, so I mean, again, like I said, there are a lot of metrics here, right? Some of them we calculate from confusion matrix, some of them using other metrics. But since we're just starting out, I only want to focus on the simplest algorithm, the accuracy for now, right? As you do other cases, I'll show you guys there are more complex metrics, right? But you can sort of, you can look at the slides to kind of understand some of the basics. Yeah. Okay. Yeah. Exactly. Yeah, we're kind of also assuming, right, that our data is accurate, right? So meaning like, we believe these tests are correct, right? So, yeah. All right, guys, let me zip through this one real quick. Okay, so now there's another thing called ROC curve, right? So remember ROC curve we talked about? I'll just do this very quickly. Remember, the algorithm gives us a percentage, a probability. How we map this to yes or no is basically up to our threshold. Right, let me go back all the way here. Yep. Remember, when I increase the threshold, when I change the threshold, my yes or no mapping will change. Yeah. And we can experiment with this one and see what's the best threshold for us. For example, let's say I'm trying to predict credit card fraud, right? I will say, okay, my threshold is 70%. My transaction has to score about 70%, whatever that score is, right? 70% score to be classified as whatever, right? Legit or fraud or something. So the threshold is within our control. And as you can see, as you change the threshold, it changes the mapping. So the way to, so which is the accurate threshold, right? So the way we do this, again, I don't want to go too deep into the sort of the details of this. There's a graph that kind of does this. It's called ROC curve, right? So we calculate true positive rate, TPR, and false positive rate. And if you're wondering where they're coming from, remember, look at the confusion matrix, right? True positive rate, false positive rate. Remember, these are the different cells, right? So based on the different cells, so this is called TPR, true positive, false positive, right? So what we do is we create a confusion matrix, we calculate the metric TPR and FPR, right? And remember, when I change the threshold, these numbers are going to change, right? Because the mapping will change, right? So to track that, what I do is I sort of change it, right? So this is my false positive on the x-axis, true positive on the y-axis. Each threshold I change, I sort of plot the results. And the result is what we call an ROC curve, right? So if you look at the ROC curve, it kind of look like this usually. It'll kind of start up, rise pretty sharply, and then kind of flatten out. So this is a good ROC curve, right? And this middle line, right? Look at the ROC curve here, right? This middle line is a random line. So we actually want the algorithm to be better than random, right? Because if the algorithm is just 50% accurate, I don't need the algorithm. I can just do a simple coin toss, right? And then determine if it's like A or B, right? I don't need to do a complex algorithm if it's 50% accurate, right? Because coin toss gives me 50% accurate, right? So my algorithm is better than coin toss, meaning like I want the algorithm to be on the top left, right? So take a look at this one. So the way we measure this, so we look at this algorithm right here, right? So here's an algorithm here, right? Here's an ROC curve. So this is a good curve, right? Meaning we want the curve to rise up quickly and then flatten out. So if you look at these, look at these curves, you can visually inspect them and figure out, okay, which is the best, better algorithm. But it's also good to have a number. Remember, in machine learning, everything becomes, at the end of the day, a score, right? A number. So the way we calculate this is another metric called area under the curve. So once you have an ROC curve created, you can actually measure the area under the curve. Remember, was it high school when we did this? We do the integration. Remember integration to measure the area under the curve. So here, you can see, if it's like a middle line, area under the curve is 50%, 0.5. Slightly higher curve, right? 0.7, and then there's a good ROC curve, maybe 0.9. So the area under the curve is between 0 and 1. Why? Because even though we can visually inspect the curve, we like to have a number so we can compare, right? Because especially when the algorithms are working, they need a number to compare against. So the way you look at the AUC is basically like a grade, right? Because if you're approaching 50%, you're failing, right? Remember, 50% is random. We want to be way better than random, right? Even though AUC can be between 0 and 1, if you're approaching 50, you're failing. So think like a grade, like A, B, C, D, right? So kind of want to be, A and B, right? pretty good grades. So that's the idea behind it. Again, if you want to look at the theory a little bit, I have some reading material for you guys. But basic idea is, right, here's a ROC curve. Once you have a curve, you can calculate the area under the curve, and that's basically between 0 and 1. We kind of want this to be within 90% and 80%. So here's like, let's end with this, right? So let's say these are my algorithm. These are the ROC curve for different it's predicting number, let's say digits, like 0, 1, 2, 3, right? And these are some other curves we generated. So looking at this curve, these are different ROC curves for different digits, right? Which digit you can see my classifier is doing pretty well. Again, if we're looking at the ROC curve visually, right, we kind of want a curve that kind of, to the left, right? Remember, that's the idea, right? We want the curve to be to the top left corner, right? And then kind of rises pretty sharply and then kind of flattens out. Exactly. So you can see then say, yeah, you know what? Yeah, 9 is doing pretty well, right? The graph is pretty good. And also, if you sort of, try to shade the area under the curve, you can see 9 covers a lot of area, right? Is that going to make sense, right? So imagine you're kind of, shading the area under the curve. 9 gives you the highest area. So 9 is doing pretty well. Followed by maybe, maybe 1 is doing okay. 5, you can see, right, is not doing so well, right? You can see the 5, right? 5 is kind of, flattening out too early. So that's how we look at ROC and AUC curve, right? So I just gave you like a very quick kind of basic understanding for both. Again, like I said, there's a lot of math and stats behind this. If you're really curious, you can kind of, study this. But basic idea is, right, when you generate a metric, say area under the curve, you can quickly see it's basically think like a benchmark number, right? For example, let's say you're taking a class, and let's say you took like 1 semester, and at the end of the semester, right, you're just reduced to 1 grade. So think of it like this. So yeah, so it's a quick way to kind of get a grade for algorithms. So okay, so now that we know the basics, let's go back to our college prediction, right? So here's my confusion matrix. Let's start with that because that's where everything starts. Remember? So my confusion matrix looks like this. Remember, admit is the one we are trying to predict. Right? Admit is 0 and 1. So we look at the confusion matrix, right? For the 0, it predicted 14 correctly, 3 incorrectly. You can see the color coding, right? For 1, it predicted 5 correctly, like say 1, 1, right? This cell 5, and 1, it misclassified. So we calculate the accuracy, right? So again, you add up the green cells, right? 14, right? So, and then sort of distribute 14, right? Plus 5, right? So 82%. And if you do the ROC curve for this one, it kind of looks like this. I mean, it looks like an ROC curve. The reason it's not smooth, right? You can see it's kind of like a little jaggedy. The reason is we don't have enough data points, so the graph is not smooth. But it's kind of follow the same pattern, right? You can see it's follow the ROC curve pattern. And if you calculate the area under the curve, 87. Remember, right? So that's not a bad algorithm, right? So it's scoring 82% accuracy metrics, and AUC is 87%. Right? So these are the metrics we'll start calculating when we do our classification algorithms. All right, hopefully I think that made sense. Yeah. So let's start with the labs. And sorry guys, let me stop here for a second for a minute, and let's see if we have any questions. So we looked at 2 important things, right? How to evaluate classifications, starting with the confusion matrix, and also kind of coming to the ROC curve, area under the curve, and all that. Again, if it's just a lot of terminology I threw at you guys, it probably is. Don't worry, we will be using these algorithms for a while, and you'll get kind of better and better. So you don't have, even if you don't get this on the first day, don't worry, right? But keep practicing these, but once you understand the fundamentals, they will start making sense. Yep. So basically, yeah, exactly. Yeah. So once you have confusion matrix, there's, like I said, there's a lot of metrics people calculate from that, like things like F-score. In some problems, you want to emphasize F-score instead of accuracy, right? Things like that. For example, things like text analytics, we look at the F-score, right? Because that's a better metric. Anyway, so it depends on the problem we are dealing with. So for now, we are going to start with accuracy. Yeah, and the kind of do some reading about the confusion matrix right here, right? Some of the terminology and some how to calculate this. It'll kind of right. It'll kind of give you right. So for example, this is a good article, right? For example, how do you evaluate metrics for imbalance classification, right? So it kind of walks you through why accuracy is not enough and all that, right? Anyway, so there's some reading material for you guys to build up. Again, like I said, we don't need to get this from day one. Right? Go back and read. Exactly. Good, guys. Let me show you guys a couple of solutions we have. Any other questions, guys? Yeah, so the accuracy is low, right? We have to go back and see, okay, what's going on, right? Why my accuracy is, right? And that's a part of the machine learning process. We do an algorithm, we run an algorithm, we try an accuracy, because that's an easy metric to calculate. And then if it's not what we want, then we have to go back and sort of, that's an iterative process, exactly. And that's what you guys are going to do, learn to do in the next few sessions. All right, guys, so here's our week 9. So I have opened up the class submissions. You can see logistic regression class submissions, and I'm going to look at 2 solutions. Randy and Yvikni, right? Thanks, guys. These are good. So let me start with those. Let's see. Do I have this one? Let me restart this. Yeah. All right, guys. So just follow the links, right? And let's see. Let me do it too. Okay. All right. When you click the link, you simply have to say open in Colab, all right? And always remember, you want to save it in your own drive, right? Just so you know, so you can modify. Yeah. All right. So this is logistic, right? So again, like I said, from scikit-learn, we are importing logistic regression, right? And we're initializing this. Okay. So get that going. And here's our data set. So I asked you guys to start with a very simple data set, just using a synthetic data set, right? Make blobs. And the reason I ask you guys to do this is because we don't want to waste any time shaping the data. So that's why. Okay. So here, make blobs, right? So if you look at the make blobs data, very simple. The way, and this is why I love scikit algorithm, right? Make blobs gives you X and Y. That's it, right? Right away it gives you X and Y, okay? And what we do is we split the data, right? So now we know all about this by now, right? So we are saying, keep 25% for testing, and it gives you 4 components: X train, X test, Y train, Y test, right? And we simply, right? Here's my logistic regression algorithm. I simply say fit my training set. Remember, right? Fitting always in training, right? And also once the training is done, we simply predict on the test case. That's it. So that's why the make blobs is pretty good, because you can do a quick regression in like 5 lines of code. All right. So let me run that. Okay. And then here's a confusion matrix. So now I have input and output, Y prediction. All right. So here's a confusion matrix, and this is the important thing, right? sklearn actually has confusion matrix built in. So all I have to do, I simply say, okay, calculate the confusion matrix for me. Here's a Y test. This is the expected output. This is the predicted output, right? And here's the confusion matrix. And you can see it's pretty much a perfect prediction, right? Because you can read the matrix, right? Remember, it's like 7, 10, and 8. They're the diagonals. They're perfect because it's a synthetic data, right? So so the algorithm does pretty well. When you plot this, you will see this, right? And this I really like this, and that's why I want to show you guys. This plot is pretty nice, right? So it's basically a right. He's using a heat map function from Seaborn, which is pretty handy, right? So you can see, right? And the reason I like this is basically you can sort of, let me see if I can make it a little larger so you can see better, right? See, predicted label, right? Actual label. So labels are 0 and 1, 2. there are 3 classes, 0, 1, 2, right? And we are predicting, right, different labels. Okay, so you can see the diagonals are pretty good, right? Because like it correctly predicts everything diagonally, so there's no misclassifications. So here accuracy will be 100, right? Because right, because why? Because there's no mispredictions. So take a look at that one, please. Yep. And the beauty of this, right? And that's the whole point. Right? Say confusion matrix, just one line. We don't have to do the calculation. It has a function to calculate this for us. And then when you do the heat map, we simply had to give this confusion matrix as input, and that's it. Pretty neat, huh? So that's one. Let me show you guys the other one as well. Randy's. And thanks guys for submitting. Because I like to feature a different one every week, right? So here's the first approach, right? Again, same thing, right? Make blobs, right? So whether creating like 2 centers, right? And then if you plot the data, this is how it looks like, right? So you see like blue and orange, and you can sort of see, can you draw a straight line through here? Possibly, right? But I'm pretty sure there's going to be some misprediction, right? Because you can try to do a straight line here, but there's going to be some plus on the other side of the line, and that's fine. But remember, in prediction, we don't get 100%, right? Unless it's like a very, very simple data set. So, all right. So let's do logistic regression here, right? Same thing here, right? So blobs x and y, and we got so again, we are extracting x and y, and splitting them into 2 random classes. Sorry, train and testing class, right? This is all pretty standard by now. And here, actually, we are scaling the data, right? Optional step, but it's a good step. But I'll come back to this one. We can try this here. Here's the training part, right? Logistic regression. And here's the training part. And you can see we are only feeding the training data, x train and y train as inputs. Okay. And then when you're predicting, we are predicting with the test class. Now, here's a confusion matrix, right? Let me see if I have a confusion matrix set here. There we go, right? Confusion matrix. Let me execute that. There we go, right? So interesting. So when you calculate the accuracy in the training set, it's 1, meaning 100%. Because remember, training set, the model sees, right? During the training, the model actually goes to the training set and learns from the training set. So it learned it pretty well. So here it's giving you 100%. But when you ask for the testing set accuracy, meaning, okay, how will you do in the testing set, it's pretty close, like 99 point, not 100%, but pretty close, 99.2. Right? And here's the one I was telling you guys about, classification report, right? So again, it's part of the scalar matrix classification report. You simply give it give the rating, what is expected and what is the prediction. It'll actually calculate the report for you, like precision, recall, F1 score, all this stuff, right? So I'll kind of skip this for now because we'll come back to this later. But like I said, you can very easily get classification report, right? Just a 1-line of code. It will calculate everything for you guys. So it's pretty neat. Okay. And here's the confusion matrix, right? So you can read this for example, right, you can see like row 1, right? There you can see there's 115 good predictions and there are 2 mispredictions. And the other row is perfect, right? There's no misprediction, like everything is 0. Right, that's why, right? You can see the accuracy is, right, just pretty high. And remember, this is synthetic data, right? Remember, this is artificial data, so accuracy will be always pretty high here, right? Unless you add some noise, like when you generate the data, you can add some noise here, right? Then, it'll kind of mix the red, orange and blue circles a little bit. Then your accuracy will go down. But by default, they'll be pretty easily separable. So pretty cool, right? So I'm showing us 2 classes. You can see they are following the same pattern, right? And this is it. Logistic regression, just 2 lines of code. The exact same, everything else is the same, right? Meaning like, getting X and Y, splitting data, they're all the same. Just change 1 line. Actually, it's pretty actually 1 line of code, right? If you compare it with the regression code just last week, this is the only change there is. Logistic. Fit, same method, right? So predict, same method. Okay, exactly. Right. So what else I want to highlight here, guys? Submission data. Good. Look at the college admission data real quick. Okay. So again, same thing now, right? So the reason I always have you guys start with synthetic data is just so there's no complication of data processing. So it'll give you the right, pretty good data. We just simply feed it to the algorithm. Now let's look at the college admission data, right? This is how it looks like. So admit column is what we are trying to predict. And these are my inputs, GRE, GPA, and rank, right? So there's all numbers, those are great. So read the data, right? Display my X, what is my input? X is my input, GRE, GPA, and rank. Very simple, right? I'm extracting these 3 columns. What's my Y? Admit column, right? Just single, right? It's going to be 0 or 1. That's it, right? So data extraction, okay? So we have 100 data points. And here's our usual train test split, okay? And so here, I noticed like Randy is doing a scaling. This is optional step, but it's a good practice to have because usually when you scale data, remember we talked about scaling earlier, right? When you scale data, usually you get better performance, right? So you don't have to scale every time. So it's a very simple step. You can simply kind of, right? You can try it out, right? You can almost comment this out, right? Because, right? You see how it's doing. He is overriding X-train with the scale data, right? So this is almost, you can always comment this out and try to say if if I don't do scaling, it doesn't make any sense, or do I get better results? So experiment very easily, and that's why Scikit is very, very easy to use. So scale the data, and then here's a create the model, and then fit the model. That's it, right? And then basically we do the transformation. Yeah. So execute that. And here's my confusion matrix. Again, you can see confusion matrix is already part of Scikit. You simply say, remember, the way to get confusion matrix is we say what is expected, what is predicted. And that's why, I really encourage the name convention, guys. See, why test, why pred. And that's why I like these notebooks because, you guys are kind of going systematically. So this way, anybody reading the code can immediately understand what these variables mean. Because if you just say ABC, it's very hard to understand what's going on, right? So always gonna stick to the convention, and and this is one I use always, right? Why why test, why pred, and here's my confusion matrix, right? And so it's a text confusion matrix, but you can still read it, right? It's not, right? Once you get used to confusion matrix, it's not that hard. But that's why I want to show you guys that you can use code as well because you can use a heat map, SNS heat map, to do a nicer display as well. Just take a couple of lines of code. So take a look at that too, right? I really like that one. So that's very, very well done. Yeah. And so look at the confusion matrix. Let's read this one. So let's look at this row. This is 0, right? So it kind of goes like first row is 0, second row is 1, so on and so forth. So if you look at the 0, yeah, right? I mean, 0, 0 is 10, 3 mispredictions. The next one is 1. So I want to see most of them under the 1 column, 1, 1, right? And yeah, I see that, right? I see 11 under the 1 column. And then 1 misprediction. Does that make sense, guys? Right? So overall, confusion matrix looks good because for the most part, my classification gets it right. But it's not perfect, right? Because I mean, if it's a, can you guys tell me what the perfect confusion matrix would have been? What would have been a perfect confusion matrix? Let's start with this, all right? So what's the perfect confusion matrix would have been in this case? Yep, so on the 0 column, it would have been 13, yep, and the other one was 0, exactly, yep. And for the 1 row, it would be 0 here, and what is it, 12, yep, right? So think of it like this way, right? So this is, right, this is 0, and this is 1. Does that make sense, guys? Yep. So, so now you guys understand what a perfect confusion matrix looks like, right? So, okay. I should probably, sorry, I shouldn't, okay, should I save this? I don't want to overwrite your solution. Give me 1 second. I did save my results. There we go, right? Good. So now we can understand, right? So now we can get the idea exactly, right? So basically, in a perfect confusion matrix, and that's why sometimes when you do the do this, kind of easy to kind of see, right? This is a perfect confusion matrix. Diagonals should have all the numbers. Everything else should be 0, right? Exactly. Yep. Close this. Okay. Good, guys. So now we get the we understand regressions, confusion matrix, right? It's looking reasonably good, right? And then and then do the report, right? So accuracy, you can calculate accuracy for both. Oh, okay. I should have run this. One moment. I'll run the whole thing. Yeah. Okay. So here's another cool thing, right? I want to highlight, make sure. Model has a function called score, right? And that's what's going to give you an accuracy. So what's the score function? Input and output, right? So here, he's doing both training and testing. That's very good, right? So this is I sort of encourage both. Remember, we have two sets: training set and testing set. Training set is what the model has gone through. Testing set it hasn't seen at all. So when you do accuracies, right? I encourage you guys to do both accuracies, both training and both testing. So X train, Y train, that's a training accuracy. X test, Y test will give you testing accuracy. Yeah. And you will see most of the time they're going to be different. Right. So imagine in a case here, right? Let's say, let me see if I can do now. Let's say my training accuracy is say 98%, but my testing is 65%. Is this a good run? Is this a good result? Exactly. So what's happening is, right, it's doing very well in training. Because why? Because the training data it sees already, right? So it has seen the data. But the testing data, it's right, it's not doing so well. Why? Because remember, the model hasn't seen the test data before at all. And that's why testing data accuracy is very, very important, because this is what matters in real world, right? Because in the real world, model is going to see data that it hasn't seen before. Right, so this is kind of a book knowledge, right? And this is sort of the street knowledge. Remember, there are two different things, right? Some people are book smart, some people are street smart, right? So we want our algorithm to be street smart, because why? This is what algorithm is going to get during when actually it's put into production, right? So it's always good to measure both accuracies, so you can quickly see it's a large gap. That's true. Yeah. So as we start doing more and more advanced algorithm, we will, before we can even do this, we'll look at correlation matrix and everything. Exactly. Yeah. 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 That's a good point, Vasily. Absolutely. Yeah. Is that going to make sense, guys? Right. So a lot of the time, mistake I see is people just measure training accuracy, and they see a large number, a very good number, and they say, yay, that's it, our model is doing really good. What really matters is the testing accuracy, right, as I explained. But I recommend you guys do both, because if you see a large gap, that basically means it's a sign of overfitting. Right, overfitting basically meaning it's memorizing, right? It's going to memorizing the data, not really learning from data, right? That's not good, because we actually want the algorithm to learn from the data, not just memorize it, right? So here it's kind of a reverse, right? You can see that it's low on training, but doing well on testing. Any guesses why this is reverse? Because you would usually you'll usually see like more on training than on testing, but here's kind of reversed. Why is that, guys? Any theories on this one? That's right. It could be a pure randomness, right? Because remember, when we do the training testing split, remember how we do this up here, right? It just just does a random split, right? So maybe your training set was hard, your testing set was a little easier. So it's kind of like this, right? Let's say you are in the class, well, your practice exam was very hard, but the actual exam was pretty easy, right? So you scored better on the actual exam than you did in the practice exam. And that's entirely possible, right? So that's fine. Yeah, so basically, remember, this is just one run, right? This is just, we are using one run. What we really want to do is we'll do a cross validation on this one, right? And that'll come later. So once you have a few algorithms, right, the best algorithm we'll decide using cross validation. Yeah, exactly. Good, guys. So so those are the two examples, right? One is like a very simple synthetic data and the college admission data. And the last one I can give you as a bonus lab. So the way you got to, and this is what I'm going to run this the other sessions, right? So you can grab some data from anywhere, right? For example, I just gave you UCI, right? But you can get it from a lot of other data sources. For example, go back here, now README file. There should be a data guide. There we go, right? So where to get data? If you look at the data section, there are a lot of repositories you can do, right? UCI, Kaggle, right? You can even use ours, right? Anyway, so get some data. The reason I kind of gave you UCI is because they are classified. Let me show you guys this one. Okay, so we go to UCI data set. Go to UCI, right? Here's the data set. So look at view all data sets here. And then you can pick the data for the type of machine learning. For example, you can say I want to do classification, right? So these are all the classification data sets. So you can pretty much get any, right? Any of the data sets and kind of try to do your classification. Like for example, and these are like, you'll see some of them are very specific to the domain. Like for example, like something will be botany or like, right? There we go, right? Here's a apartment for rent, for example. Let's see what that is, right? And you can read all about, right? You can read all about what are the attributes, right? And you can download the data as well, right? So that's why I like this one. We first, choose which you are trying to do classification, and then look at all the data sets available, then pick one. You need to kind of understand it though, right? To basically, work on the data. So that's why, there's tons of these. You can pick any one of them. So that's why I don't want to restrain you guys to just one data. You can pick any data. Yeah. So some of the data sets have, they will describe what's included, right? Some of them is kind of, not as well. So you kind of want, like, for example, maybe like let's say the breast cancer diagnosis, right? Let me see, this data is pretty good. And they will actually give you, right? What are these attributes, right? So as you can see, right, this is some good real world data, and you can get those. So what I recommend is, the way I'm going to do this is, for each section, I will ask you guys to choose your own data, right? Because that's something you got to get used to as well, because different data has different processing patterns, right? So I just gave you guys this one as a kind of an example to start with, because this is basically income data. Let me look at this one. It basically, given the attributes, right? So you see, right? Age of the person, where do they work, what kind of education they have, bachelor's, master's, and all this stuff, right? Race, based on this. So the idea here is, it's a classification. They're trying to predict whether this person's making more than 50,000 or less than 50,000. Yes or no, right? So basically, you can say, okay, my classification here is going to be, given the data, it's going to say yes or no. Yes meaning yes, making more than 50K, or no, making less than 50K, right? So the good news is that the data is pretty extensive. You can choose as much as you want. For example, and let me look at the right. You look at the printout. It's a pretty elaborate data, right? And you will see a lot of the data is categorical. Like for example, race, sex, right, marital status. So now you guys know how to deal with this, right? Because we run the algorithm, we have to sort of convert them to, right? Convert them to categorical data, right? And Scikit will do this for you, pretty quickly. But what you can do is you can sort of start with like just numbers data for now, right? So for example, here you can say, right, let's say capital gain, right? Maybe you can start with education numbers. Just start with something simple, right? And even they actually even assign weights, because remember, this is like census data, right? So they they do a pretty thorough job The weight, I need to go back and look at this. I think this is a weight for each measure or something like this, right? So you're supposed to multiply the weight. But again, since we're just experimenting, you can ignore this for now and just have a simple attributes. Right? So this is pretty cool. I say, see the scatter plot, right? So you took like, age and education, right? And then looked at the salary, right? So salary is basically, the red, what is it like? Blue is less, orange is more than 50K, something like that, right? So it's kind of a 3D data, right? Plot using 2D graph. That's pretty cool, right? So age is on the x-axis, education on the y-axis, and how do we? But we have to represent three-dimensional data, right? I need to say whether this person making more than 50K or not, right? So you can say orange is more than 50K. You can see this, right? So you can kind of see, like, you kind of draw a border like this, right? Kind of like this, saying, okay, if you're young and your education kind of in a lower level, you're probably not going to make 50K, right? But if you have education is pretty high, let's say you have an advanced degree, right, master's, PhD, something like this, right? Then you sort of start earning pretty quickly over 50K, right? And then as you get older, you're kind of making more and more because you're getting promotions and so on and so forth, right? So you kind of sort of see a dividing line, kind of like like a diagonal like this, right? But also you see outliers. You see here's an outlier. Here's like a person in the 20s, right? And the education not that high, but they are making more than 50K. And that's bound to happen, right? So you will never get a most likely not get a clean 100% accuracy, but yeah, that's the idea, right? How you guys can talk through and all this stuff, right? So anyway, is that going to make sense, guys? Kind of the very basic idea, right? So again, if you look at the data, right, you can see you can choose what your x and y are going to be. So here x is just two attributes, age and education. Because why? Because then I think he did a smart thing because that, right? These are numbers, right? Age and education, right? So you can start with those. And if you want to include others, like for example, you want to include mental status, or you want to include, say, race, you had to basically encode. Remember we talked about one-hot encoding and all that, right? Exactly. So then it gets a little bit more involved. But still, I want you guys to start looking at the data, because these are the kind of data you will get in your real world life. Okay. So go through the logistic, fit the logistic, right? There we go. Get the accuracy. Yeah. So kind of around 70s. Yeah, high 70s. That's to be expected. Yeah. But still pretty good, right? Just by using two attributes, age and education, right? You can achieve like about 78% accuracy. That's not bad at all, right? So now you can. So now this is your baseline. Now you can do better, right? Now you can add other attributes to say, okay, which one influences more? Is it race? Is it ethnicity, right? Or is it sex, right? Right? Or gender, right? You can kind of keep going. Exactly. So confusion matrix, you can see, right? So you can see like most of them are categorized correctly. Actually, this is good. Right? Actually, let's take a look at this one. Let me do this here a little bit. This is a good confusion matrix. Let's talk about this. So this is 0 column, and this is 1 column. All right, so this is 0 actual. Again, you're kind of, right, and then 1 actual. And then here is 0 predicted, and then 1 predicted. Okay, so hopefully this makes sense, right? You can sort of, that's how you kind of look at this matrix. So let's see. All right, guys. So let's look at the matrix. How is it doing with zeros? Is it doing good? What do you guys think? Look at the matrix, and that's why I can reformat this a little this way so we can actually read it. Look at the matrix. How is it doing in zeros?
It's over 99% good.
Yeah, zeros is predicting pretty well, right? Because remember, actual 0 is predicting most of them as 0. That's good. Only a few of them are misclassified as 1. Okay, so you guys know my next question. How is it doing on ones? Remember, horizontal row is actual, and the columns are predicted. So what do you guys think? How's it on 1? Yeah, right. It's not doing so well on 1. You can see, right? It actually is basically misclassifying a lot of ones as zeros, right? Because it's only it's like 500 or so, right? Actual. So like for each correct classification is basically misclassifying 3 as zeros. You see that? Yeah, exactly. It's only right. So each one I have 3 here, so only 20% good. So as you can see, right? I just say, hey, accuracy is 78%, but that doesn't give you the full story, does it? Right? See, look at the recall. Right? So that's why you should, because, and this is why I'm spending some time on this one, guys, because you shouldn't be fooled just looking at one number and then saying, oh yeah, I'm getting 80% accuracy, that's good. The real actual story, you have to really dig into the numbers. And that's why, when you print the confusion matrix report, the classification report, like I said, right? It prints out, precision, recall, F1 score. Remember, go read about all this, right, in my slides. And for ones, right, meaning, what is the one? One is above 50K, right? The scores are pretty dismal. See, 25%, 28%, I can say, right? And F1 score is pretty small as well. But for under 50K, it's doing pretty well. You can see, right? Under 50K, the scores are pretty high, 80%, 94%, 87%. But over 50K, it's not doing so well. Yeah. Interesting, huh? So, so that's why confusion matrix, we're going to start simple, but I'm kind of pushing us a little bit here into look at a little bit more, a deep look at the numbers. Yeah. So now you got to go back and say, aha, this is what I'm getting. Why is it not doing so well on 1? Now you got to go back and look at other attributes. Because why? Because remember, we just gave 2 attributes as input, right? Age and education. And then you look at the data set, there's so much more, right? There's education, right? There's mental status, occupation, gender, race. There are so many things you can include. Yep. Exactly, right? So what you want to do is you want to basically start adding more attributes. Now you can just throw attributes, right? Some of the things are categorical. So you have to go back and look at your previous labs, see how to encode the categories into numbers or one-hot encode, and only give those encoded columns, right? So it'll take some time, and remember, and if it takes some time, just realize it's just the way it is, because a lot of the times, remember, machine learning, you're spending time shaping the data, right? The actual machine learning is basically, just these 2 lines, right? Logistic regression and fit. That's it. And that is, that's assuming once you have X and Y figured out, this is the easy part. Figuring out X and Y is where you're going to be spending a lot of time. And that's why I want you guys to start working on different data. Yeah. Yeah, actually, yeah, we should do a correlation matrix too. Actually, let me see if I can do one real quick. And adult data. Let me see if I can do a correlation matrix real quick. All right. So, yeah. So, right. So you can see, sort of see here. Let me see if there's anything obvious comes up. Capital gain, capital loss. No, okay, yeah. Oh, and here's another thing, right? And it's only looking at numbers, right? Because it doesn't look at the other columns. So you have to kind of do some extra work to get the full correlation matrix. Yep. But this is good. I mean, this is very, this is a very good starting point, right? I kind of want you, and this is real world data, and that's why I kind of gave it as a bonus lab here, because you have to kind of start with this and start working on this. Now, here's how I kind of recommend for everybody to do this. I mean, start with the census data, because this is a good data set to kind of, and it has a lot of things going for it. Start with that, right? And like Randy did here, start with numbers. right? Let's start. This is very simple. Start with numbers, then start adding features, and keep a record of, for example, remember the housing data we kept record of, if we had this variable, this is our score. So this way, when you iterate through different attributes, you will know which ones give you better results. Yeah, good. Let's see what else I want to highlight here. And this is good. So this is this is the final result thing. So anyway, confusion matrix, how to read it, right? Look at the report a little bit also, look at, different categories of reports, right? So kind of start getting into it. Now, homework for you guys is look at the data column, right? Look at the data guide. And this is what I want you guys to do on your own. For all the algorithms we are going to learn, I'm going to have you guys pick a data set, right? Let's say, that's why I like UCI, because UCI has, all these things classified already. You can say, I want a regression data set, I want a classification data set. So pick one data set. And whatever that is your data set. I want you guys to try all the algorithms on the same data set. Is that going to make sense? Don't switch data sets between algorithm, because we want to keep the algorithm data set stable and then plug in different algorithms, right? Kind of like Legos, right? So we got to keep the same shape, but you can sort of plug in different algorithms, because that's going to give you a pretty good insight on how to test algorithms very quickly. Because you will find a lot of the real world data, you're going to spend a lot of time shaping the data, right? Once that is done, that's it, you're done, right? Then plug in the algorithm, as you can see right here, right? Algorithm is just 2 lines of code. Very, very simple. So start with that. All right, guys, so that's it. Now, the lesson we did for categorical conversion is basically, which one is that? On the variable encoding, feature engineering 2. Okay, this is what you want to look at to understand variable encoding. And scaling the data, which Randy used. Very good work, Randy. Feature engineering 3. Right. So look at these, do some reading. You can look at the exercises, right? But you can sort of see here now how everything is coming together, right? It's kind of like, that's why I say Lego today, right? Because you guys kind of done the individual parts already. So now you're kind of putting them all together, right? So for example, right, in this lab, you're doing encoding, you're doing scaling. And then finally, right, once you're done all the basic work, right, finally, you're doing the algorithm fitting. So that's why you're thinking about this. And trust me, you're going to be spending a lot of time in these two. Actually, probably encoding, right? Or the data cleanup. Actually, I should say you'll get a lot of time in this one, and also this one, right? 70–80% of your time is going to go here. Oh, scaling optional, right? Because some algorithm will ask you to scale. Like for example, the one algorithm we are going to look at this week, SVM. Basically, you have to scale because the algorithm kind of expects it, right? So they will say in the documentation, when you read the documentation, it will say, this algorithm expects data in a scale format. Then that's your answer. Yeah, you have to scale it. And the scaling is, honestly, pretty straightforward, right? Just a couple of lines of code. Where was this, right? Yeah, right, that's it. So I would say, and again, this is no right or wrong answer. I always say, when in doubt, just scale, right? Just add some code so you can turn it on and off, right? So for example, if you don't like it, you can just simply comment it out. So it doesn't hurt to scale. I mean, there are corner cases you don't want to scale, but that's fine. We'll look at them some other time. So scaling is not a bad idea. Yeah. When it's scaling, remember scaling all the X features. Remember, and that's for the good thing, because when you're doing a scaling, when you're doing like say here, Randy's using standard scaler, it will basically look at all the coefficients and scale them all. Yeah. So it basically will do the work for you automatically. Remember, we talked about this. They try to fit everybody in like the bell curve, zero centered and everything, right? They will do all the math work for us. Yep. Yeah. So typically, like I said, scaling is a good practice, right? It's like flossing, right? We always say we should do it, but we don't do it all the time. Anyway, right? So good, guys. So summary. We are into, look at the big picture. We are into classifications, right? So classification is like a different mentality than regression. So I want to make sure you guys understand the basic stuff like, what are the algorithms, confusion matrix, right? All the terminologies. Read up on this. And when you guys do your labs, right? So I'm going to give you some simple data for you guys to work on. And each of you is going to pick your own data set, right? Wherever that is, doesn't matter. It can be from UCI, it doesn't have to be from UCI. You can go to Kaggle as well, right? Look at the data section here. I give you plenty of pointers. Pick one and then stick with it. Remember, because I want you guys to know the data very intimately. So whatever data set you guys are picking, you're going to use it for the next few algorithms. Okay, so that's why it's important. I'm kind of emphasizing this, right? Make sure you pick a good data set, but not too difficult because you don't want to be discouraged, right? So, and there's no like a right? How do you say? There's no like a right or wrong data set. So pick one that's going to work for you guys. Same thing, right? Even SVM, I follow the same pattern, right? Basic readings, right? Look at some code, right? By the way, this book, I don't know if anybody's reading this book. It's a pretty good book. So here's my right. Here's my right. Here's the book here, right? Introduction to Statistical Learning, right? A free book. So we go to chapter 9 or something, right? If you look at the index, they have a pretty good coverage of SVMs, support vector machines, right? So 337, right? So there we go, support chapter 9, right? Support vector machines. Again, they'll kind of walk you through some of the math, and right, if you're curious, you can look at that. I really like their diagrams. They are pretty good diagrams, right? So if you want to sort of overlook the math, that's fine. Look at the diagrams. They explain it pretty well, right? Again, the link is right here, guys, for you, right? It's for you, chapter 9 of the book, Introduction to Statistical Learning. And then go through the checklist, make sure you understand the concepts, and then same thing, right? Exercises, right? Now, for the exercise, I kept the same data, synthetic data first, college admission data again. Why? Because I want you guys to learn the algorithm first, not waste time, fiddling with the data, right? So that's why the first two are the exact same as logistic regression. Third one is up to you guys, right? Like I said, remember, this is your data set. You're going to pick one and study it, clean it, right? Shape it, and then that's what you're going to be using for all the following algorithms. Okay. So you don't have to. This is just an example, right? So I don't want everybody to kind of just use census data. Please pick your own. Okay, so all right, guys. Is it clear what we are going to be doing? So this week is SVM. We are going to start looking at different algorithms on the right. So just like that, we are looking at where was that? There we go, right? So we just did logistic. Next one is SVM. We'll do naive-Bayes, KNNs, right? I want to cover a few classification algorithms, and then we'll go into decision trees. Okay. All right, guys. Any questions? So as you will notice, things will go pretty quickly now, right? Because like remember, like we are kind of all building on we are learned already. So we kind of put in the hard work already. Now it's basically experimenting, and now it's the fun part. So you will see we'll go through algorithms pretty quickly, right? So thanks for sticking with us. And I got an email from one of my friends. Actually, he enrolled in, and then he kind of dropped out in the halfway. He said, "No, I don't have time to do all this reading." So I understand. It takes a lot of takes some effort, right? Because if you're just just watching me speak, you're not going to learn much, right? That's why I'm really pushing you guys to do reading. So my goal here is kind of steering you guys to like think like a little like a minefield, right? I'm walking through the right path, but you had to do the walking. So I can only give you a map, right? So that's why. So hopefully you guys like the format. Let me know if this is too much work, too little work. We can always adjust. Okay. Yeah. Good, guys. That's it. So I know it's late for some of you, so thank you, guys. Again, practice, right? Please, right? So if you have limited time, and if you're going to spend it in some time, rather than reading like sort of theoretical books like this, I would rather have you guys practice more, right? And then go back and read the theory. It'll make a little bit more sense. Right? Somebody asked me this, like, should I brush up on math? Not right now, right? Unless you have some time, practice first, go through the exercises, kind of want to get the practical sense of how the algorithm works, then you can go and look at the theory. Yep. So, good guys, that's it for today. Anything else? Very good. So you guys know the drill. You guys have the assignments for next week already, so keep at it, and same time next week. Yeah. Thank you.